Chapter 10 of The ABC of Atoms by Bertrand Russell. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. The ABC of Atoms. Chapter 10. Radioactivity. Shortly after the discovery of X-rays, the world was startled by the discovery of radioactivity. The discoverer was the French physicist Becquerel. What first led him into the discovery was the fact that a very sensitive photographic plate was put away in a dark cupboard with a piece of uranium, and was found afterwards to have photographed the uranium in spite of the complete darkness. On investigating this remarkable phenomenon, Becquerel found that the rays which produced the photograph came from the uranium itself, and did not depend upon any previous exposure to light, as is the case with fluorescent substances. Uranium was found to be able to produce rays out of itself apparently indefinitely, and these rays were very powerful. At first the discovery was upsetting. It seemed to go against the conservation of energy, because the energy radiated by the uranium was to all appearances created out of nothing. This turned out not to be the case. The energy, as we shall see, comes out of the nucleus of the uranium atom. But something equally astonishing was found to happen. In radioactivity, one element turns into another. Throughout the Middle Ages, chemists had tried in vain to transmute elements. The impossibility of doing so seemed to be one of the most certain results of chemistry. This had proved to be a mistake. In radioactivity, atoms of one element throw out particles from the nucleus and become atoms of another element. Radioactivity is associated in popular thought with radium, but the fact that the discovery of radium was caused by that of radioactivity, not vice versa. Monsieur and Madame Curie, who were working under Becquerel, observed that pitchblende, from which uranium is obtained, is more radioactive than pure radium. They inferred that it must contain some very radioactive constituent much more active than uranium. This search finally led Madame Curie to the new element radium. Since then, a number of new radioactive elements have been discovered. Summerfield, opposite page 56, enumerates 40 of them, and there is no reason to suppose the list complete. Before going into the process by which a radioactive atom disintegrates, let us consider the rate at which different radioactive substances decay. The atoms of radioactive substances are like a population which has a certain death rate. In a given time, a given percentage of them die, and are born again as atoms of different substances. But they are not endowed, like human beings, with a certain span of life. Some live a very short time, and some a very long time. The old ones are no more liable to death than the young ones. So far as we can tell, any population of atoms of a given radioactive element will lose a certain proportion in a given time, quite regardless of the question whether the atoms are old or young. It is customary to measure the rapidity of disintegration by the length of time that it takes for half a given collection of atoms to die. This period varies enormously from one substance to another. Uranium, which is only very slightly radioactive, takes 4,500 million years, in its most stable form, for half of its atoms to decay. The first product of their disintegration is a substance of which half decays in just under 24 days. This breaks down into a substance for which the period is less than a minute and a quarter. This next substance has an uncertain period, estimated at 2 million years. At this stage, two different products may be formed, one of which in turn becomes radium, of which the period is 1,580 years, while the other becomes protoactinium, of which the period is 12,000 years, the next product being actinium. Radium gives rise to the inert gas niton, also called radium emanation, for which the period is a little less than 4 days. The end of both series is a form of lead, which, so far as we know, is not radioactive at all. There is a separate family starting from horicum, which has the atomic number 90. This also ends in a form of lead, atomic number 82. Some radioactive products decay so fast that half of them die in a tiny fraction of a second. The shortest time is estimated as 100,000th of a millionth of a second, but this is more or less conjectural. It must not be supposed that if half of the atoms of a substance die in a certain period, all will die in double that period. After half are dead, only half as many are left to die. Of these, half will die in the next period. Thus, to take radium. Given a certain number of atoms of radium, half decay in 1,580 years, and half are left at the end of that time. In the next 1,580 years, half of that half will decay, and a quarter of the original number will be left. At the end of a third period of 1,580 years, an eighth of the original number will be left, and so on. The exact circumstances which make a radioactive atom break up are not known. We only know statistical averages. we have to suppose that the nucleus is in more or less unstable equilibrium, and may be disintegrated at any moment by some chance which comes, on the average, to a certain proportion of the atoms at any given period. We are in the same position as we should be in human populations if we could observe the death rate, but we're quite unable to observe the various diseases of which people die. One point in which radioactive substances differ from human populations is that, at the beginning of the series, we have two substances, uranium and thorium, which sometimes die but are never born, so far as our knowledge extends, while at the other end we have three kinds of lead, which are born but apparently never die. Thus the heaviest elements in the periodic series are continually breaking down, and no process is known by which they can be built up again. There may at one time have been many elements with a structure more complex than that of uranium, which have broken down so that whatever traces of them are left in the universe have not been discovered by us. Radioactivity is one of those processes of degeneration, in a certain technical sense, to which no converse process of regeneration is known. We see complex atoms breaking up, and it is natural to suppose that there are, or have been, circumstances under which they are put together out of simpler atoms. But no trace of any such circumstances has been discovered. In this respect, as in some others, the universe seems like a clock running down, with no mechanism for winding it up again. All the uranium in the world is breaking down, and we know of no source from which new uranium can come. Under these circumstances, it seems strange that there should be any uranium. But if, like some insects, we lived only for a single spring day, we should think it strange that there should be any ice in the world, since we should find it always melting and never being formed. Perhaps the universe has long cycles of alternate winding up and running down. If so, we are in the part of the cycle in which the universe, or at least our portion of it, runs down. Everything pleasant is associated with this running down, because it is only this process that liberates energy for the purposes that we regard as useful. It is time, however, to return from these speculations to the mechanism of radioactivity. When a substance is radioactive, it emits one or more of three kinds of rays, which are called respectively alpha rays, beta rays, and gamma rays. It has been found that alpha rays consist of particles, each of which is the nucleus of a helium atom. Beta rays also consist of particles, but in this case they are electrons. Gamma rays do not consist of particles, but are on the nature of light waves, only with a very much higher frequency, higher even, sometimes 20 times higher, than that of X-rays. We need not further consider the gamma rays, which do not concern the transformations of the nucleus. It is the alpha rays and beta rays that produce the results in which we are interested. We will begin with the alpha rays. The alpha rays are compounded of alpha particles, which are nuclei of helium, and thus have a positive charge double that of the hydrogen nucleus, and a mass or weight 4 times that of the hydrogen nucleus. They are shot out with a velocity which may reach to nearly 1/10 of the velocity of light. Since they have a double positive charge, they attract electrons, and therefore it is not surprising that they tear away electrons from any atoms they may meet, and so cause the matter on their path to become positively electrified. When they have captured the 2 electrons that they desire, they become ordinary unelectrified helium atoms. Being small and heavy and swift, they have great power of penetration through ordinary matter. They come from the nucleus of the atom, which thus loses 2 units of positive electricity, and therefore is moved down 2 places in the periodic series. At the same time, the atomic weight diminishes by 4 because the helium nucleus is 4 times as heavy as the hydrogen nucleus. If the alpha particle left the electrons of the atom undisturbed, there would be an excess of 2 electrons in the atom after its departure, but in fact, it generally tears away at least 2 electrons as it goes. If it loosens more than 2, the atom will become positively electrified until it can annex free electrons from its surroundings. In the end, it settles down into an ordinary unelectrified atom of an element whose atomic number is less by 2 than that of the original atom. Thus radium, which has the atomic number 88, sends out alpha particles and becomes niton with the atomic number 86. A substance may, however, be radioactive by sending out beta rays instead of alpha rays. Some substances send out one kind, some the other, a very few can send out either, and can thus give rise to 2 different products of disintegration. The beta rays are simply very swiftly moving electrons, the most swiftly moving matter known to us. They attain velocities which reach very nearly the velocity of light. They have been known to travel at the rate of about 297,000 kilometers a second, while light covers 300,000 kilometers a second. A kilometer is about 5/8 of a mile. The velocity of light is a theoretical limit which cannot be attained by anything material, so that we have in beta particles velocities about as great as we can ever expect to find in nature. Since radioactivity always gives rise to a new element, and since the element is determined by its nucleus, the beta particles as well as the alpha particles must come out of the nucleus. Since the beta particles are electrons, this shows that the nucleus of a radioactive element must contain electrons. This is to be expected in all elements, because the atomic weight increases about twice as fast as the atomic number, so that the atomic number, which is the net charge in the nucleus, must be the result of a number of hydrogen nuclei about twice as great as the atomic number and a number of electrons about equal to the atomic number. This is not always exactly true, but at any rate it is likely to be a first approximation. There is therefore no reason to be surprised by the fact that electrons come out of the nuclei of radioactive elements. When an electron comes out of the nucleus of an atom, it increases the net charge in the nucleus by 1, and therefore increases the atomic number by 1. Thus it is possible for the atomic number to be increased by the loss of something from the nucleus, provided what is lost is an electron. But although the atomic number is increased, the atomic weight is not. The electron weighs so little that its loss makes no appreciable difference to the atomic weight. Moreover, since the net charge on the nucleus is increased by 1, the atom will secure another planetary electron as soon as possible. Thus, in the end, the effect of a radioactive change by the emission of beta particles ought to be to leave the atomic weight unchanged while increasing the atomic number by 1. The result of one emission of alpha particles followed by 2 of beta particles is thus to deprive the nucleus of a helium nucleus and 2 electrons, without in the end changing the atomic number. Thus uranium has 2 very stable forms, called uranium-1 and uranium-2. Uranium-1 is the great-grandfather of uranium-2. Uranium-1, by means of alpha rays, gives rise to uranium-X1, of which half decays in little less than 24 days. Uranium-X1 gives rise to uranium-X2 by means of beta rays. Half of uranium-X2 decays in just over a minute. Uranium-X2, by means of beta rays again, gives rise to uranium-2. Uranium-1 and 2 both have atomic number 92. Uranium-X1 has atomic number 90, and uranium-X2 has atomic number 91. Thus the 2 stable forms of uranium have the same atomic number, although they have different atomic weights, 238 and 234. Again, the various radioactive series all end in some form of lead. The 3 forms are called respectively radium-lead, actinium-lead, and thorium-lead after their respective ancestors. These all have the same atomic number as ordinary lead, 82, but their atomic weights differ. Ordinary lead has the atomic weight 207.2, radium lead 206.0, thorium lead 207.9. It is probable, however, that ordinary lead is a mixture of 2 or more kinds of lead, and perhaps this is also the case with what counts as thorium lead. The reason for this view is that it is now probable that every perfectly pure element has an atomic weight which is almost exactly an integer. When 2 elements have the same atomic number, they are called isotopes. Apart from radioactivity, the only discoverable property in which isotopes differ is atomic weight. They have the same net charge in the nucleus, and therefore have the same number of planetary electrons, and the same possible orbits of the electrons. Consequently, their chemical properties are the same, their optical spectra are the same, and even their X-ray spectra are the same. All this is as it should be according to theory. It is no wonder that the existence of isotopes remained so long unknown. They first became known through observations of radioactive products. But it has lately become known, through the work of F.W. Aston, that there are many isotopes in regions of the periodic table where radioactivity can hardly be supposed to take place. Aston found means, in a gas containing atoms of different weights, by which he separated the heavier and lighter atoms. He thus obtained 2 pure gases out of a mixture which had hitherto been wrongly supposed to be pure. The result was to show that atomic weights are very approximately integers in many cases in which this was thought not to be the case. Thus neon, which has the atomic weight 20.2, is found to consist of a mixture of 2 gases, one having atomic weight 20, the other 22. Chlorine, which has the atomic weight 35.46, is a mixture of 2 kinds having atomic weights 35 and 37 respectively. Krypton turns out to consist of as many as 6 isotopes, xenon of 7, 2 of which, however, are more or less doubtful. It is a curious fact that in radioactivity, the particles thrown off by the nucleus consist always either of electrons or of helium nuclei. Not only do we never find nuclei of heavier elements than helium thrown off, but we never find hydrogen nuclei. This is surprising, and as yet no adequate explanation has been found. What is to be said on this subject belongs to our next chapter. The energy displayed in radioactivity is colossal. It shows that within the nucleus of the atom enormous forces are concentrated. This is not surprising when we consider that an atom as a whole is very minute, and that the nucleus of an atom is enormously smaller than the whole atom, that within the nucleus of uranium about 238 hydrogen nuclei and about 146 electrons are packed together, and that these attract or repel each other with a force which increases as the square of the distance diminishes. The energy involved is shown by the incredible swiftness of alpha particles and beta particles. To make a body move with the velocity of light would require a strictly infinite amount of energy, and is therefore impossible, not only in practice but in theory. Therefore, to make ever so tiny a body as an electron move with a velocity 99% of that of light requires a very great amount of energy. Before the theory of relativity, the kinetic energy of a moving particle was taken to be half the mass multiplied by the square of the velocity. Nowadays, this has to be changed to allow for the increase of mass with velocity. In the case of a velocity 99% of that light, the mass is increased about sevenfold, and the kinetic energy in the same proportion. The energy of the alpha particles, owing to their greater mass, is even more than that of the beta particles. As Sommerfeld says, the sources of energy which are thus disclosed to the external world are of quite a different order of magnitude from the energies of other physical and chemical processes. They bear witness what powerful forces are active in the interior of atoms, the nuclei. This world of the interior of the atom is in general close to the outer world. It is not influenced by conditions of temperature and pressure which hold outside. It is ruled by the law of probability, of spontaneous chance which cannot be influenced. Only exceptionally a door opens, which leads from the inner world of the atom to the outer world. The alpha or beta rays which come out when this happens are envoys from a world which is otherwise closed to us. In the next chapter, we shall give an outline of the few facts which can be ascertained about this small fierce world, the nucleus of an atom. Optical spectra have told us about the outer electrons, X-rays about the inner rings of electrons. About the nucleus itself we know very little, except what can be learned from radioactivity. End of chapter 10.